He's the ACM ICPC World Finalist. He's also a longtime teacher in Excellence. Okay, thank you, Yibo, for coming. Turn the stage to you.
All right, great. Yeah, so let's go over the goal problems here. Oh wait, okay. Yeah, so for our three goal problems, we had Cowdependence, Interstellar Intervals, and job completion. So the knowledge required for the first problem is like square root decomp, binary search, and or ad hoc. For our second problem, we have a relatively standard dynamic programming problem with some optimizations needed. And for the third problem, we had a greedy. Now, the XCAM courses that covered all this knowledge are going to be 400, 401, 602P, and 602. Okay, let's go over the actual problems themselves. And I'll go over them in order of like easiest to hardest, in my opinion. So I think the easiest problem of this contest was probably the third problem, job completion. For this problem, we're given a bunch of jobs, and for each one, we choose to complete it or not. And if we choose to complete it, we have to start it at or before some time s of I, and it takes t of I time to complete. So this problem, if you try to just solve it in this format, is actually kind of tricky. Let me give an example. So suppose you have one job that you can start at time 1, but takes 10 units of time to finish. And you have a second job that you can start at time 3 and takes 1 unit time to finish. One idea might be, well, maybe you can sort them all by start time, but it turns out this actually doesn't work that well. Because what you would have is if you start this, if you schedule this first task to be started at time 0, for example, then you can't schedule the second one. But there's actually a way to fit both if you were to schedule the second one within your first time slot, and then schedule your next one in the next 10 units of time. And so this is a case where it can be very, very tricky to do, even if you do like some sort of sort by start time and then some DP on if you should take it or not, it doesn't quite work, right? Okay, and then similar problems happen if you try to like go backwards in time. So the big observation for this problem is that we actually don't want to deal with the start times. We want to deal with them in terms of deadlines. So let's just briefly convert this problem statement a little bit. So if we're given the deadlines of every project and the time it takes to complete them, then we would have this first project's deadline is at time 11, and the second one is at time 4, right? So this is the exact same problem. All we've done is we've added the time it takes to the start times of each project to get the deadlines of each project. And now we can sort by the deadline time. And now it makes sense, for example, to use like a DP solution to figure out for each of our projects, should we take it or not? Okay, so this would be an idea you can use to get the first or like inputs 3 and 4. So you can do some sort of DP on the index and how much time has already passed. Okay, and I think you can do something very similar for the n is up to 2000 case, where basically you can still DP on time and index, but the time dimension, you probably need to like corner compress or something to make it work. All right, so let's go over how we actually solve this whole problem, which is once we've sorted them by deadline, we notice that like in general, since all the tasks are weight 1, as in you only get 1 point for completing any task, in general, we want to do this like fastest jobs first, right? So one idea could be you can now sort them based on their timeline, or like their time to complete and go through them in order of like smallest time to largest time and try to add each one. But it turns out it's still a little bit tricky to figure out how to schedule them to make that work. So instead, we'll do this another way where we sort by their deadline. And essentially the idea is for every single task, we're just going to try to take it whenever possible. And whenever it's not possible to take a task, we can kick out an existing task that we've taken previously, as long as that task that we kick out takes more time. So let's go through our example here. Let's just add maybe, let's see, let's add, okay, let's add some. So let's say we have 4, 1, 11, 10, and then we also have like 12, 4, 13, 7. Okay, something like this. So first of all, our optimal solution should be to take this task, and this task. But that being said, the optimal solution, if you only have the first two tasks, would be to take the first two. So yeah, we need our algorithm to work regardless of if it's like just this prefix of the array in our input or the whole entire array, right? So let's essentially try to compute the optimal solution at every single step. So the first thing we see is this task of time that's due at time 4 and takes 1 unit of time to do. So let's just go ahead and do it. Okay, then we get to our next task and we see, okay, we can actually do this task because now our total time needed is 11 and this is due at time 11. So we can just take both. Great. Now for our next task, we see that we can't schedule all 3 of these because this takes a total of 15 units of time, but this task is due at time 12. So what we're going to do is we're going to kick out the task that took the longest to do so far. And now we can add in the new task. Right? And now we still have 2 tasks, which is the best we can get among the first 3 elements. But our total time taken is now only 5 as opposed to 11. So it is like the most optimal solution up to this point. And then finally, for our last task, we can just go ahead and add it in because this now takes a total of 12 units of time and we have 13, right? So we can output 3 for this example. Okay. So quick note about like some implementation details. So first of all, the data structure we need to figure out what's the, so first of all, yeah, so we're going to keep like a priority queue to track all the tasks that we've taken so far, and they'll be sorted based on how long it takes to complete them. And then whenever we try to add in a new task, what you can do is you can just always add the new task into the priority queue and also increment the total amount of time that it takes. And then if the amount of time it takes total is going to exceed the amount of time so far, then you can just take out the biggest element out of this priority queue and decrement your time by that amount, right? So let's just run through this really quick one last time with our example here. So here's our priority queue. We loop through the first element, and then our total is currently 0. So we loop to the first element, we add it into the priority queue, update our total, and we see we don't need to kick anything out. Go to the second element, we add in a 10, and now our total is 11, and we still don't need to kick anything out. Now for our third element, we just go ahead and add 4 into our priority queue, and now our total is 15, which exceeds this 12. So we have to take out the biggest element. Let's go ahead and remove the 10 from our priority queue and also decrement our total by 10. And then finally, we get this element. So we just add in a 7 and our total is now 12. So we don't need to kick anything out. And then at the end, our answer is just whatever the size of our priority queue is. Okay, yeah, so that was problem 3. I think probably the easiest problem of this goal contest, assuming you've seen some sort of similar greedy problem before. If not, if this is like the first time you're seeing this priority queue greedy technique, it can be very tricky to figure it out. Let's go over the first problem from this contest, which is Cowdependence. So for this problem, we have Farmer John's and cows arranged into a line, and each cow has some label A of I. And then what we need to do is we need to output for every single value of X, the minimum number of groups it takes, such that every cow is in exactly one friend group. and cows of the same ID have to be like friends with each other. Okay. So for this problem, let's start with a O of n squared solution. So given a fixed value of x, so let's just say we set x to be 2 here. We can just go through the whole entire array and greedily assign the groups, right? So whenever you get a new ID, you have to put that cow into a group. So for this one, we have to put it in a group. So therefore, we'll start 1 here. And then for this one, we see that, oh, there's already a group that was started at index 0. So they can just go in that same group. And the same thing with this one. You can also go in that group. And then we get another +1 at this 9. Another +1 at this 2. So we have to start a new group. For this one, we check the previous one group, and it's too far away. So we just add another one. Maybe let's start this. And then similarly, this 2 does not need a new group. This 1 does not need a new group. And finally, this one does. So that's how we get that for x equals 2. You get an answer of 5. Right. And so if we just run this for every single value of x from like 1 to n, our overall runtime is n squared. Okay, so now let's look at the subtasks. And it turns out the subtasks here are kind of telling for what you need to do for this problem. So the first thing is, what if we only had up to 10 unique IDs, right? So essentially we have a bunch of like big groups of cows, and there's only 10 distinct IDs. We just need to figure out how to group some, like a few big groups. And then for our next subtask, no like ID is repeated more than 10 times. So basically we're gonna have a lot of small groups of cows, and we also need some algorithm to figure that out. And then the idea is probably along the lines of, if we figure out both of these subtasks, maybe we can just merge the two solutions for the full problems. Yeah, for the full solution. Okay, so let's start with the case where a of I is less than or equal to 10. Okay, so let's go ahead and use B to denote the number of group, or B to denote the size of your groups. So in this case, B is roughly, or it's like at least n over 10, okay, so most of your groups are going to be quite large. So let's just say, yeah, B is really large. Okay, so how do we solve like for a big group the answer? Well, one thing is we can actually just brute force each group on its own. So let's say in this case we have a bunch of 1s, right? Let's just go ahead and get the indices of all the 1s. So we have a 1 at index 0, 1 at 2, or 0, 1, 2, and then. Okay, so these are the indices of all of our 1s. And if we just store this in like a set or a vector and sort this, then we can easily simulate the number of groups needed just for this ID, right? So let's start with x equals 1. What you can do is you can just start at the first count, make it a group, and then you can use binary search or like upper bound, lower bound to find the next place you need to start a group. So you start a group here, then this can cover everything in the range 0 to 1. So you next need to start a group at 2, right? Okay, so you start another group here, and then you start another group, and that's it, right? So this would be 4 for x equals 1. And then you can do this for x equals 2, and so on and so forth. And the key thing to note is that as x is increasing, the runtime of our algorithm gets much faster. So in the worst case, let's just assume you had every single index in your group. Then what happens is when you have x equals 1, if B is the size, it takes us around B over 2 iterations, right? Because you can only group them into like groups of 2. And then when x is equal to 2, you get like B over 3 iterations needed. Because this would be the first group, this would be the second group, so on and so forth, right? Okay, and so essentially what we have is we can analyze our runtime using harmonic series here. Because this effectively we have like B over 1 plus B over 2 plus B over 3, so on and so forth. All the way up to like B over n. Okay. And, or I guess let's just analyze this in terms of n. So assume you're like, you just have one big group. Okay. And this would just be n log n. in terms of the number of like binary searches we need to do throughout this whole sequence. Okay, so we figured out that our runtime is at most like n log n or n log squared n if you had exactly one group. So if you have only like 10 groups, then what we can do is we can just do 10 times like n log n or n log squared n, and that gives us our solution. So essentially for our first subtask, all we need to do is simulate each group individually, and that's going to be fast enough as long as you use this jumping method or binary searching to jump to the next group. Okay. So next, let's take a look at our subtasks when the size of our groups are really small, right? So each label appears at most 10 times. All right. So the idea here is now, let's say we have like a few positions. So like 0, like 5, like 30, and like 100. So let's say these are the indices where like ones appear, right? And we want to figure out what the answer is for each value of x from 1 to n. So it'd be very, very wasteful to just like simulate the process for each value of x, because one thing we can note is that the answer doesn't change that often. As an example, if you picked x equals 1, your answer is going to be 4, because each cow will be in their own group. But even if you pick x equals 2 and 3, your answer is still 4, because every cow still needs to be in the same group. So what we can do is we can just figure out, well, let's just figure out for every single answer, what range of x gives you that answer. Okay, so let's write it out here. So for our example here, if you want an answer of 4, right, then your range of x can be anywhere from 1 to 4. Yeah, because if you pick 1, or even if you pick up to 4, every cow is going to be in their own group. Okay, what if you want your answer to be 3? Well, then the minimum value of x you have to pick is going to be 5, because if you pick 5, then the first 2 cows will be put in the same group. And so this answer will only be 3. And now it turns out we can actually go up quite large, up to 29, and still get an answer of 3. Right. Okay, and then similarly, we can do the same analysis for, well, when will the answer be 2? And in this case, yeah, so you start from 30, and you can go all the way up to 99. Because, yeah, so if you pick 30, this will be in one group, this will be in a second group. Even if you pick 99, that's still the case, right? Now, finally, if you want to answer 1, you need to pick at least 100. And then it doesn't matter what your upper bound is. So let's just say up to n, right? So we can figure out the ranges in which, or like the ranges of x for every single answer. And the thing is, because there's not that many elements within each group, like this is going to be bounded to 10, right? So if we can just figure out all the ranges for each of these 10 possible answers, then we can pretty quickly compute the answer. And then just one last note about how to actually compute this, like to output the final array. What you can do is once you have all these ranges, you can think of this as you just want to add like 4 to this range of x, add 3 to this range of x, add 2 to this range of x, and add 1 to this range of x. And you do this for every single group. And so you can use like any data structure you want, but one way is to just do a difference array, because we're just statically adding some like range, and then we care about what the array looks like at the very end. Okay. Yeah, so that's how we can get our 8 through 11 test cases, where everything only appears 10 times. Oh, sorry, one quick note about how to actually get these ranges. What you can do is you can just binary search for the range in which the answer is 4. Yeah, so basically, if our target is 4, we can binary search on value of x from 1 to n. Let's say first we tried 50. We can just evaluate what the answer would be with x equals 50, and we see, oh, it's 2. So if our answer right now for 50 is 2, and we're trying to get the answer to be 4, we know we have to decrease the value of x to try to get to 4. So next we can maybe try 25. And we see, okay, 25 is a 3, so we have to go even lower. Maybe we try 12. 12 is still a 3. Then we try 6. 6 is still a 3. And then we can try 3. 3 is now a 4. But what you want to be able to find is the lower and upper bound of this. So there's a few ways you can do this. You can either run like 2 binary searches, one to find the higher end, one to find the lower end. The other thing you can do is you can go backwards. So we know that for the answer of 1, one valid answer is definitely n, right? So if you set your answer, or if you set your value of x to be n, you're definitely going to have 1 as your answer. So then you can just binary search for the lower bound of what 1 would be. And we find that it's 100 in this case. Now this automatically gives us the upper bound of our next answer. So we know since 100 is the lower bound for 1, we know that the upper bound for our next range is at 99. Yeah, so then we get this 99 for free, and then we just have to binary search for the lower bound of that range, which is 30 in this case. And then again, we get 29 for free, and then we binary search for this 5, and so on and so forth. Okay, and yeah, another note is that these answers might, like, for every single possible answer, there might not exist a range. Let's see, as an example, okay, so here's a simple example. Let's say you have like a 1 at position 2, another 1 at position 3, and another 1 at position 5. The answer of 3 doesn't exist because the lowest you can go is 1. And even if you use 1 as x, you still get only 2 groups, right? So that's a simple example where like the answer being 3 doesn't exist, but this could happen for any of the numbers in the range from 1 to like size. Okay. Cool. So next, let's go over how we can combine these two solutions. So there's a few ways you could do this. The most typical square root like decomposition idea is let's just set some threshold b to be square root of n roughly. And if your group is larger than b, so basically if you have some ID and there's more than square root n occurrences of that ID, we can just use the algorithm we used for our inputs 4 through 7. And if the number of elements is small, aka less than b, then we can just use the algorithm we used for when it's small. Okay, and let's quickly analyze the runtime for why this actually runs in time. So first of all, if your group is big, we know that the worst case runtime of a given group is n log n, or n log squared n. This is assuming the biggest group you can possibly have, which is like a group of size n. Okay, and the maximum number of big groups you can have is at most square root n. Because each of our big groups is, or let's just use b here. Because each of our big groups has at least square root n numbers, so we can have at most square root n big groups. So the total runtime of our big groups is at most n square root n log squared n. Okay, now let's also analyze our small groups. So for our small groups, we're also going to do an upper bound runtime here. So to do each singular small group, the runtime is b squared log n. Because we're going to binary search on each answer from 1 to b. And then so that's how many binary searches we're running. And for each binary search, of course, there's log n iterations. And to complete each run, our worst case runtime is b log n. It's actually quite a bit smaller than this, but worst case is like you go through the elements one by one, and each time you're doing a binary search, so it's b log n. Okay, and so if you go ahead and multiply this by the number of groups you can have of the small group, it's n over b, where b is like the size of your small groups. And then, so this can cancel out. And we get n times b times log square root n. And then finally, b here we set to b square root n. So this is our upper bound for our small group runtime, and this is the upper bound for our big group runtime. Yeah, so this would be our overall runtime. And this is a very rough upper bound. I think with some more careful analysis, you can find that it's actually faster than this. But regardless, this is like good enough for 10 to the 5, especially knowing that the constant factor is really good and that this runtime is done assuming you could, like for some given value of x, you had to loop through all the elements one by one, which we know is not the case, especially for larger values of x. And then an alternative solution, so this works, and the alternative idea is we can actually just not worry about the big small group thing, and we only run the small group algorithm. Now, the problem with the small group algorithm is that if you have like a really big group, and you're binary searching over all the possible answers, so when you binary search for all the possible answers 1 through n, what's going to happen is you're going to repeatedly run the calculation for a given value of x. So yeah, so for example, when you start your binary search on, okay, when is the answer 1? You first computed it for x equals n over 2, and then you went either down or up, and so on and so forth. And then when you do this for when the answer is equal to 2, you're going to do the same thing, right? You recompute what it is at n over 2, then you might go smaller or larger, but then you probably also recomputed that one, and so on and so forth. So what we can do is if you just cache all the results, so basically for any given value of x, if you've computed it before, just don't compute it again. So it's sort of like a memoization DP idea. Then this guarantees that what's going to happen is you have exactly n log n calls on your like evaluate function. And each position of the, like for every single given value of x within a group, it can only be evaluated once. So then we still have the nice harmonic series runtime analysis to keep our runtime manageable. And in that case, the runtime, it's still hard to upper bound, but the runtime is quite good. And the upper bound is definitely going to be O of n squared root n times log squared of n. Yeah, so this is still the rough upper bound. But if you actually implement this and submit it on USACO, the maximum test case was only like 500 or 600 milliseconds. This passes very comfortably. Okay. Yeah, so that's it for this problem. Overall, it's like kind of an ad hoc problem. Square root decomp problems don't show up that often, but I guess in this case it did. All right, for our third and last problem we'll be discussing, we have interstellar intervals. So essentially, for this problem, you're given some string, and these are the constraints. So what happens is you start with like a blank canvas, and for every single cell, you can either paint it white and go to the next cell, or you can paint it some like R followed by Bs. So like smallest one you can do is just 1 R followed by 1 B. You can also do 2 Rs followed by 2 Bs, and so on and so forth. And however, you're not allowed to go over the end of the array. So for example, if I paint the first cell to be white, and then I want to paint the next 3 cells red and the next 3 cells blue, that's not legal because we've ran out of space on our canvas. Okay. And essentially for this problem, for every single cell that's the R in the input, your final canvas has to be an R there. For every cell that's an X, it could be any color you want. And for a B, it also has to be a B. And we need to output the total number of distinct ways we can color this canvas, satisfying all those properties with some modulus, because the answer can be really large. Okay, so first of all, this problem is a very classic, or like right away when you read it, it just feels like, okay, it's probably going to be dynamic programming. And some like signs is like, well, first, we have this output the answer mod 10 to the power of 9 plus 7. Whenever this happens, it's almost always DP because you can't like iterate through the number of like combinations. So you kind of have to do some sort of like DP to make it run fast enough. And also we get like a very clear state, right? So the state could just be the index. And this could mean a couple of things. The way we're going to define our state here is the index means how many characters you've already colored in your canvas. So let's go through maybe this example here. Or yeah, so let's say the letters are X, X, R, B, X, X. Then your indices go from 0 all the way up to 6, or up to n in general. And the idea is, if I've considered 0 elements, then my answer is, of course, 1, right? Because there's just one way to have an empty canvas. Okay. And now for every single character, what we're going to do is we're going to think about how many ways are there to transition to here. And we'll actually think about this in both in terms of like push DP and pull DP. And you'll see why that's useful in a second. Okay, but let's start with the pull DP idea, where we're going to try to compute DP of I. And we are already given all the values of dpj less than I. And we'll just transition from them to build up our answer. Okay. So the first thing is, if this cell is an X, then one thing we can always do is just paint this current cell white. And so what that means is we can always transition from dp I minus 1 and add that to our answer. So let's go ahead and mark it as 1. Okay. And then from here, there's not anything else we can do, because we can't paint this to be B and this to be R, because that like goes out of, like we don't have enough room on our canvas so far to paint like RB. So that's it, right? And if we just analyze this prefix of our answer, it makes sense. So if we have an empty array, the answer is 1. If we have a singular X as our input, our answer is also 1, because the only thing you can do is paint it white. All right. Now for the second X, we still have our transition of, let's just paint this white. So we'll go ahead and just add dp I minus 1 to our answer. And now it's a bit more interesting because we can also choose to paint this to be RB. And so we can also transition from index 0. So let's go ahead and change this to 2 now. And if we do a quick sanity check, this checks out because it can either be white, white, or it can be RB for a canvas of just like 2 X's, if that was our input, right? All right, so let's go over to our next cell here. So this cell is a bit more interesting because it's an R. And so the first thing to note is our first transition doesn't work because we're not allowed to paint this white. So we're not going to add dp of I minus 1. And then the second thing to note is the other transition we have is we basically want to pick some like number of R's and B's to paint that ends here. And again, there's no possible transitions because you can't paint this to be blue, red, right? And similarly, you can't paint this to be like blue, blue, red, red. Well, for 2 reasons. One is you don't have enough space on your canvas, and 2, it's guaranteed that this has to be red. So there's no valid transition here. So therefore, the answer just stays at 0. And again, if we do a quick sanity check, this makes sense because if our input was just XXR, then the number of ways to paint this is in fact 0 because we can't paint a red without painting a blue in this problem, right? Okay. For our next cell here, we have a B. And again, first we try to paint this cell to be white, but because it's not an X, that's not a valid transition. The next transition we can do is, well, what if we paint like a B here and a red here? That works. So we can go ahead and transition from this cell. And that gives us an answer of 2. Cool. And then we can also try to transition like 2 blues with 2 reds. And we see that doesn't work because that would violate this cell's constraint. And then finally, quick sanity check here. Our answer is either like white, white, red, blue, or red, blue, red, blue. All right, and those are our 2 ways to color this. Nothing else. Okay, and now finally, we can just basically do the same thing for the last few cells. So we start by painting this white. So we'll just add 2 from this transition. Then we can try to do like BR. That doesn't work because that violates this. However, we can do 2 B's followed by 2 R's. So this is a valid transition, and that will be transitioning from here. So we're going to go ahead and mark this as 3. Okay, and then finally, we have this cell. So again, you can paint it white, so that's +3 already from here. And then you can also paint this to be BBRR. So again, +1. You can paint this to be B here, R here, and therefore we get +2. And then the final transition that we can do is we can paint 3 Bs followed by 3 Rs. And so that'd be another +1. And that gives us our answer of 6 here. Okay. And this dp that we described as is currently O of n to the third. And let's analyze this real quick. The reason is we have O of n states. And for each state, we have up to n transitions to try, because we can try painting this white. We can also try to paint the last one blue and a red before that. We can also try 2 blues, 2 reds, so on and so forth, up to like n over 2 blues and n over 2 reds. And then we have a final factor of n, because let's say I pick like 2 blues and 2 reds. I need to check if any conditions are violated, right? So in this case, we can see that, oh, the 2 blues, 2 reds doesn't work because it violates the blue that we need on index 4. And that's where our O of n cubed comes from. Okay, so let's start by getting our runtime down to n squared, which would pass the next 2 test cases. And what we notice is that we can pretty easily trim out the last factor of n. So basically, we want to check if the conditions, like if we can paint some number of blues and reds, and we want to do this check in O of 1. So one easy way to do this is you can just compute a prefix sums of all the R's and another prefix sums of all the B's. And then you can just check within the range you're painting, like within the red range, are there any blues? And within the blue range, are there any reds? If there are, then it's an invalid transition. Otherwise, it's valid. Right? So now our algorithm is basically the same, but we still have our n states, and we try all n transitions, and we check which ones work in O of 1. And that's n squared for our 5 and 6 test cases. Okay, and so far we've been talking about this in terms of pole DP. And let's just quickly analyze, like, how can we speed up our transitions, right? So how do we know which transitions are valid? For pole DP, let's say we're trying to compute the answer to some dp of I here. And let's just for now assume that it's like an x. Then our first transition is we can transition from dp I minus 1. And this check is simple. It's just, is my current cell x or not? So that one we don't really need to worry about. So let's go over the harder ones to check, which is all the possible like number of blues followed by reds we can do, right? So like, does 1 blue, 1 red work? And then does 2 blues, 2 reds work? And then does 3 blues, 3 reds work? And so on and so forth. And so basically we're checking, like, do we meet the condition for I minus 2? Do we meet some condition for I minus 4? Do we meet some condition for I minus 6? So on and so forth, all the way down to 0. Right. Okay. So now, well, let's break up our condition, which is essentially what our condition is doing is we're going to paint some range blue and we're going to paint some range red. And within the blue section, we need to make sure that there's no reds. And within the red section, we need to make sure there's no blues. It turns out one of these is pretty easy to check, right? So if you consider the range of blues we're painting, we're always going to be painting one more blue for every different transition. So we start with 1 blue, then we ask, like, for a range of 2 blues, are there any reds? And then for this range of 3 blues, are there any reds? And so on and so forth. And essentially, the first time we find a red, that's going to cap the number of times we can paint blue, right? So let's say there's a red at I minus 3. Then we know the max we can do is we can do 3 blues and no more than 3 blues, because if you do 4 blues, that's definitely going to have a red in it. And 5 blues is also definitely going to have a red in it, and so on and so forth. Okay, so this part of our check is relatively simple. We can just find the first red to our left, and that caps the upper bound of our value of x for our transition. Now, the other one's a bit trickier. So let's suppose there's some like blue here at index I minus 2. Well, then your first transition, 1 blue, 1 red is fine. But then when you try to do 2 blues followed by 2 reds, this is not going to work. But then when you do 3 blues, or maybe let me write this, BR is fine, BBRR is not fine. But then starting from 3 blues, this is fine again. Right? So this makes it a bit tricky to figure out which transitions exactly are usable or not. Okay. Cool. So to summarize for now, when we do pull DP, it's really easy to check for our current range like of X, or like how many blues and reds we're going to do in a row if it satisfies the blue constraint. But it's hard to check if it satisfies the red constraint of like whatever red range I'm painting, make sure there's no blues in it. Okay. Let's go ahead and do the same problem with push DP. So let's just quickly go over our sample one more time. So if we're trying to do push DP now, essentially we're going to start from some DPI that's already been computed, and we push to all the transitions we can transition to. So let's go ahead and do this for the empty array first. Well, first of all, we can paint the first letter white, so we can transition it here. We can also paint this red followed by blue, so we can transition to here. We cannot do 2 reds followed by 2 blues, because that would violate this one. But we can't do 3 reds followed by 3 blues. So we can also transition to here. Right. Okay. Cool. So that's going to be all the states we transition to. So we just push our DP value to them. So this gets a 1. This gets a 1. Wait, sorry. This gets a 1, I mean. And this gets a 1. All right. Next, we're here. And we do the same thing. You can paint a white here. So you can just transition this. And then you can also do red, red, blue, blue. So you can also transition to here. And that's it. All right, so this becomes a 2. This becomes a 1. Let's just keep going with this. So from this state, you can't paint the next one white, but you can do a red followed by a blue. So this becomes a 2. You can't do RRBE, so we're done here. This answer is 0, so it doesn't really matter what our transitions are. Here, similarly, we can paint this white. We can paint this to be white. We can also paint the next ones to be R and B. So we have 2 transitions here. So we change this to 3, change that to 3. And finally, starting from this cell, the only thing you can do is paint the next cell white. So you add your DP to their DP, and you get 6, just like before. Right. So this is the exact same thing, pretty much, except we're just doing push DP. And let's think about the advantages of push DP. So if I'm currently at some index I, and again, let's just assume this is an X, doesn't really matter. Well, one thing is one transition is we go to I plus 1, and this only works if the next element's also an X, right? So again, this is simple, so we won't really worry about it. But let's consider the harder transitions where it's like we're going to put some number of reds followed by some number of blues. So again, maybe we do 1 red followed by 1 blue. Maybe we do 2 reds followed by 2 blues. Maybe we do 3 reds followed by 3 blues. And so on and so forth. And we want to know for each of these transitions, is it valid or not? Okay. Well, let's try to take care of the easy case first again. So let's say I see a blue here at index I plus 3. Okay. Okay. So what that tells us is the maximum number of transitions we can do is only 2, because we can do RB, we can do RRBB, but starting from like 3 Rs and 3 Bs, it's going to be invalid. And same thing for 4 Rs and 4 Bs, that's also going to be invalid, because the first blue to the right of us dictates the maximum range we're going to be valid for in terms of what transitions we can push to. Right. Okay. Now we can actually also think about this in reverse. So what this means is this is going to cap which indices can transition from us. So if we're at index I and we find a blue 3 indices away, let's do a concrete example here. So let's say our current index is like 2, and there's some blue at index 5. Well, what this tells us is we can do 1 R followed by 1 B. So like index. Right. So what this tells us is index 4 we can transition to. We can do 2 Rs followed by 2 Bs. So index 6 we can transition to. But starting at index 8, we can no longer transition to them. And vice versa. If you're at index 4, you can transition from 2. If you're at index 6, you might be able to transition from 2. But starting at index 8 and 10 and so on and so forth, you cannot transition from index 2. Right? Okay. So effectively, what we can do is we can think of this as, so let's go back to thinking about this as just pull DP, but we also considered how push DP works. And so this tells us, like, for this DP value of I, we can no longer add this answer to some future answer if they exceed, if they're at index 8 or further, right? So what we can do is we can just mark an event to say, okay, at index 8, I need to remember that DP of 2 is invalid now, because from index 8, you're not allowed to transition from index 2 based on this blue cell that we found here, right? Cool. So what we can do is we can just add an event that says at index 8, I'm going to go ahead and change my DP value at index 2 to be 0. All right. And then the second thing is, let's say I'm currying from index 8, right? And let's say there's like a R at 6. So what this tells us is we can do 1B followed by 1R. We can do 2Bs followed by 2Rs. But we cannot do 3Bs followed by 3Rs and so on and so forth. So this like from our pole transitions, the first R to our left of us is going to dictate like what range we can transition from. And if you have no R's, then you can transition all the way from the start. And your DP of I's stores all the valid transitions. So if there's a invalid transition due to this B being here, then we would have set the DP at index 2 to be 0. So now what we can do is we can just safely range sum query this. Okay, so let's take a look at example here. So if you're currently at index 8, you can just range sum query from 6 and from 4. Okay. If this R was moved a little bit further, so let's say this R was here, then this means you can go up to like 4Bs followed by 4Rs. So that means you can go to 6, you can go to 4, you can go to 2, and you can go to 0. And you're just going to sum up all these elements. And now realize that we're not going to be overcounting our answer, because although like 3Bs followed by 3Rs is not a valid transition, right? This is not a valid transition. That's okay that we're still adding the elements at DP of 2, because we've already processed the event that says DP2 is no longer a valid transition for all future like DP values. So we've actually set it to 0, right? So when we sum this element from here, it's not hurting us. Cool. Yeah, so there's a few ways you can implement this. The first way is you can treat your DP array instead of as just a normal array. Just use a binary index tree. Because if you think about the two operations we need to do, basically we need to be able to set some elements, and we also need to range some query. And binary index tree allows us to do both. And this gives us a O of n log n runtime. Yeah, so essentially just sweep from left to right. At each DP of I, you calculate at which index it'll stop being a valid transition, and you add an event to set it itself to 0, starting from that index. And then the second thing you do is, based on where your first red to your left, that tells you what range you're allowed to range some query from. So again, the example here is if you're at index 8 and the first red's at index 4, you can query anywhere from 0 to 8. Let's say you were at 8 and they're at like 7. Then the only thing you can query from is 6, right? Because you can do BR. So let's say you are a red, then there's nothing you can query because there's no number of Bs you can put, right? Okay, so you can basically take the difference between the first R to your left and your index, double that, and that's the range of valid queries. Now, one other thing is we only want the indices with the same parity as us. So for example, if I'm currently at like index 8 then I only want the sum from 6 and the sum from 4 and the sum from 2 and the sum from 0. I don't want the ones from 1, 3, 5, 7, right? Similarly, if I'm at index 9, I only want it from 7, 5, and 3, and so on and so forth. So what you can do is you can split your DP array into 2 separate bits. One bit can store the odd indices, and one bit can store the even indices, and then you can just query from the correct one. And then one last note is this current runtime is in log n. You can also implement this in O of n with like a 2-pointer idea, and I'll explain how that works. So let's take our example from, let's say the current DP of I is a R, right? Then basically what this means is you're gonna be resetting your answer. So whenever you get an R, your answer is automatically 0. And the valid range that you can query is just like nothing, right? You can't query anything. Okay. Now think about what happens when you move 1 to the right of that. Let's assume this is not R. So let's just assume this is an X. Well, then essentially your range of valid queries goes from nothing to just 5, right? And then what happens if you move 1 more? So let's say now you're at index 8 and the previous R was at 6. Well, now your range of valid queries extends 1 more. So now it goes from like, it includes this 4. So effectively, as you're moving along, as you're iterating through I, assuming you don't get a new R, then your range of valid queries just goes left by 1 every single iteration, right? And then whenever you do hit another R, you just reset your DP value 0, and your range is reset back down to nothing. Just nothing. Okay. So that's how you can basically do this with like sliding window or 2-pointer, where like every iteration you don't find an R, you increase your window size by 1. And then whenever you do find an R, you reset your window size to 0. And this way, as you're increasing your window size by 1, you can easily just add the new element to the cumulative sum rather than doing like a range query. So basically, you're still doing that range query, but you're just pre-computing what the range sum would be as you move your window 1 by 1. And then the other thing to note is, let's say you also have to deal with the fact that some DP values expire. So let's suppose what happens is you're currently at index 8, and that means your valid range of queries goes up to 4. But let's say at index 9, your new valid range of queries goes up to 3. But what happens if like one of the DP values expired? So let's say DP value of 5 expires at 9. Well, whenever you get one of these expiration events, you need to check, is that value currently inside your range of like valid transitions? And if so, not only do you have to set this DP value to be 0, you also have to subtract whatever it was. So let's say it was 3, you change it to 0, and you also subtract 3 from your cumulative sum of your like window. Yeah, and so if you do this, you can do this problem in O of n, and you don't need to use a binary index tree. So I think this is probably slightly easier to implement, actually, if you think through it first, and it runs faster. Cool, and that's all the problems for this goal contest.
Thank you, Yibo. Thank you for spending time with us to share the solution. I have a last slide to share with the team. I think all of you might know XAMPP have achieved pretty good results. And let me share my screen here. USACO contest, XAMPP, we have more than 300 students achieved the USACO silver and above, more than 60 students in the platinum division, and 27 joined the finalist, while 2 EDOI medalists and 1 RI good medalist. All of them got this, 3 of them got MIT offers. Last year, we have 11 students received MIT offer. Here are the classes we provide. We have on-site camps. It's coming. in December 26th, in 2 weeks, and it will 1 week in the South Bay, San Jose. We also have a summer camp. It's 10 days from the end of July. We have a year-round weekend classes. It's 4 quarters a year, 10 weeks per quarter. In addition, we have USACO mock test. This is also important to help you to prepare for the USACO. We have grandmaster classes for the USACO Gold, Platinum Camp, and the IOI. If you are interested in EPCS, you might try our EPCS class. Okay, great. That's all for today. If you have any questions, you might email us or visit our website. Great. Hope you enjoyed the USACO contest. It's a long journey for you to come to the USACO Gold level. Congratulations. Sometimes it's a challenging task. Hope you enjoy that and keep improving your coding skills. If you are lucky to pass USACO Gold, that's a great milestone. If not, I think you should feel very confident and comfortable with your achievement. You're already here. You can pass Google interview without any doubt. The algorithm and the data structure interviews. Okay, great. Thanks, Yibo, again. So hope all of you have a good week and happy holiday. Thank you. Bye.